Hello, welcome to section 1.5, complex numbers. We will use complex numbers to solve different problems, including quadratic equations and real-world problems. I have to tell you that so far we've had these nice solutions where we have like x squared equals 4 and we take the square root of both sides and we get x equals plus or minus 2. But complex numbers actually open the door for us to solve all different types of quadratics. For example, if I had x squared equals -4, then I wouldn't be able to solve this at first. I would say it's no real solution. But after what you learned today about imaginary numbers, you will magically be able to solve it. And I say magically sarcastically. They are called imaginary numbers, but they do exist in the real world, and they have helped us to have things like cell phones and computers and all sorts of things. We will need to review, though, the simplified radicals before we start this. So just a reminder, if I want to simplify the square root of 27, I can break it apart by making a factor tree. And then I would be looking for groups of 2 since it's the square root. And so I would end up with 3 square root of 3. Or I can think of 27 as 9 times 3, and I look for the perfect square in 27, which is 9. And the square root of 9 is 3, so I end up with 3 square root of 3. And then for number 2, I know the square root of 36 is a perfect square, and so that would just be 6. For number 3, I can break apart 48 by making a factor tree, or I can look for the perfect square in 48. So I'll try to kind of show you both methods here. And this is a reminder. We've already done this, but it's going to help with what we're doing today. So if I do the prime factorization, I'm looking for groups of 2. It looks like I have 2 groups of 2. So a 4 would come out, because that would be 2 times 2, and I'd be left with a 3. Or I know that 16 times 3 is 48, and 16 is a perfect square, so I end up with 4 square root of 3. And then number 4 is very similar. I can break apart 75 as 25 times 3. The square root of 25 is 5, so this would be 5 square root of 3. If I do the prime factorization of 75, I get 5 times 5 times 3, which allows me to take a 5 out, and a square root of 3 is left over. All right, so now let's talk about and define I. So we call I the imaginary unit. We've learned that some quadratic equations have no real solutions. However, we're now going to be able to find those no real solutions by using I. So I is equal to the square root of -1. So this allows us to solve all quadratics. Mathematicians created it, and we call it the imaginary unit. So for example, if I had like the square root of -5, instead of saying it's non-real, which it is, now I can just take an I out, because this would be like the square root of -1 times the square root of 5, and then that would be an I. And so the square root of -5 is the same thing as I square root of 5. All right, and then if I had like the square root of -4, that would just be 2I. So anytime we have a negative inside the square root, we take out an I. Also, I squared is equal to -1. And so these are just kind of like 2 definitions that we just have to take as they are, all right? And you probably actually have I in your calculator. So you might look for that special symbol in your calculator. And that might help you with some of the problems we do. All right. Now, I is the imaginary part, but we also have what we call a complex number. So A and B can be real numbers. The number A plus BI is called a complex number, and it is said to be written in standard form. The real number A is called the real part, and the real number B is called the imaginary part of a complex number. When B equals 0, the number A plus BI is a real number. When B does not equal 0, the number A plus BI is called an imaginary number. A number of the form BI where B does not equal 0 is called a pure imaginary number. Let me explain by showing you a few examples. If I have 5 plus 3I, then 5 would be considered the real part, And I, the 3i, would be considered the imaginary part. And together, we would call this complex. But if I just had the number 7, then you can think of there like being an invisible plus 0i here, which means that if I just have the number 7, and remember this is invisible, then of course 7 is just a real number, right? But if I have something like 9i, that would be considered a pure imaginary number. Okay, so one of the first things we're going to do is we're just going to simplify with complex numbers, and that will lead us to some applications a little bit. So let's start by simplifying radicals that are complex. So you can see that in each of these, we have a negative inside the square root, right? And so that means that we're going to have an I as part of our answer. So first, I have the square root of negative 16, but I know that the square root of negative 1 is equal to I. So I can actually take out that negative by putting an I at the front, and then the square root of 16 is 4. So the square root of negative 16 is just 4i. In fact, if it was the square root of negative 25, it would just be 5i. And if it was the square root of another perfect square, like the square root of negative 49, it would be 7i. Okay, so that's what it looks like when it's a perfect square. When it's not a perfect square, like 70, I can still remove the negative by placing an I in the front, and then I would factor down 70. Now, as I factor 70, I'm looking at this and I realize I can't take anything out. It's 7 times 5 times 2. There are no perfect squares in 70. So actually, there is nothing else I can do. I can just leave it as I square root of 70. All right, letter C. I have a negative, so I'll take that out the I, and then I'm going to reduce the square root of 48, which we kind of already did earlier in this video. And if you remember, we were able to take out a 4, and there was a 3 left over. So this would be 4i square root of 3. And if I worked that out, it would look like this. If you wanted to do the prime factorization, it would look like that. I would take out a 2 and a 2, and that's how I would get the 4i, and then a 3 would be left over. And then for letter D, I have negative 5 plus, and then this piece right here, the square root of negative 9, I'm definitely going to have an I because of the negative. And then the square root of 9 is 3, so this just becomes 3i. So this would be negative 5 plus 3i. Right. The set of real numbers is a subset of the set of complex numbers as shown below. So like we've already talked about, we've got the real numbers, we've got the imaginary numbers. They create what we call complex numbers. This is true because every real number A can be written as a complex number using B is equal to 0. That is, for every real number A, you can write A in the form of A plus 0i, which I kind of already alluded to a little earlier on. All right. So one of the things we do in this class, which everybody really enjoys, is adding and subtracting complex numbers. And the reason why is because it's very easy. Real goes with real. Imaginary goes with imaginary. Very convenient, all right? This is really fun and easy. So for letter A, 4 is going to go with 1. So 4 plus 1 is the real part. So 4 plus 1 is 5. Okay, and then for my I would have positive 7i plus negative 6i. So 7 plus negative 6, so that's for my i's, right, would be positive 1i. And since it's a positive 1i, I'm probably just going to put a plus I, because that would just be assumed to be a positive 1 in front of the I. Why don't you try letter B? Feel free to pause the video. All right, so 1 plus 3 would go together. Let me highlight this for you. 1 plus 3 is 4. And then I have positive 2i minus 2i. Oh man, that cancels out. Cool. I just end up with 4. And like I said, if you have I in your calculator, you can actually type it in with parentheses, and it should help you if you need help with this, but because it's kind of fun to check it with your calculator. So you should look for that little I key. Okay, let's move on to multiplying complex numbers. Remember that I squared equals -1. Okay, so let's start with letter A. I'm just going to use the distributive property. 4 times -2 is -8. 4 times 3i is 12i. I am done. Can't do anything else there. But for letter B, it's like a binomial times a binomial. So I'm either going to use my distributive property or I'm going to make a box. So I will show you what it would look like with a box. And then on the next one, I'll use the distributive property. All right, so in the first box, so if you're doing the distributive property, you just do 2 times that and then -i times that. So 4 times 2 is 8. And then in this box, 4 times -i is -4i. In this box, 3i times 2 is +6i. And in the last box, 3i times -i squared is -3i squared. Okay, but watch what happens here. So I have 8 minus 4i plus 6i minus 3i squared. First, I can combine my i's together, right? So the -4i plus 6i would give me +2i. All right, so that's going to become +2i. But also, now this is a little tricky, I can simplify this because I squared is equal to -1. Okay, freaky. So I squared gets replaced here with a -1. And so this actually becomes 8 plus 2i plus 3, and then I can combine 8 plus 3, which is 11. So this becomes 2i plus 11, or 11 plus 2i. Whoa, that's crazy, right? So just remember, I squared equals -1. So if I have 5i squared, that would equal -5 because this I squared would get replaced with a -1. Okay, so let's try letter C. And I will do the distributive property this time. So I'm going to do 3 times all of this. And then I'm going to do 2i times all of that. So I'm just applying the distributive property. So 3 times 3 is 9, minus 6i plus 6i minus 4i squared. All right. I combine my middle terms. Now you might have guessed, since these are conjugates, the middle terms actually cancel out, and I'm left with 9 minus 4i squared. Also, I know I squared is equal to -1. So really it becomes 9 plus 4, which is 13. Now what's really cool is if you have a calculator, you type this in, it's really neat, because you'll end up with 13. Let's talk about complex conjugates. So if I have a plus bi and I multiply it times a minus bi, the middle terms will cancel out, and I will end up with a I squared, which will give me a -1. And so the result ends up being a squared plus b squared. And that actually happened on the previous problem that we just did. So to write the quotient of a plus bi and c plus di in standard form, where c and d are both not 0, we multiply the numerator and denominator by the complex conjugate of the denominator to obtain this result. Now don't worry, we're going to naturally do this together anyways. So we don't, like just how we couldn't have a radical on the bottom, we also can't have an imaginary number on the bottom. So I'm going to give you a few examples before we do some of your homework. So like, for example, if I have 5 over 2i, then to get rid of I could just multiply by I over I, right? And the reason why I would do that is to get rid of I in the denominator, because this will become 2i squared, but I squared is -1, so then that I squared would become a -1 times 2, which would be -2. And then on the top, I would just have 5i. Let's try another one. So let's say that we had 6 over 7i. Well, then I could just multiply the top and bottom by I over I, because remember, we're just trying to get rid of that I. And so when I do that, I would get 7i squared and then 6i on the top. And what happens is the I squared cancels to -1, and so I end up with -7 and 6i. So 6i over -7. Of course, an advanced example would be if I had 2 over 3 plus I. Now the reason why this would be advanced is because I have a binomial now. And so in that previous slide, or actually on this slide, sorry, they were telling us to multiply by the conjugate. So the conjugate so I take the denominator and I want to write the conjugate, which would be 3 minus I. And I'm going to multiply the top and bottom by 3 minus I. Okay, so let me start with the denominator, because that's more difficult. Okay, so for my denominator, this is what happens. I have 3 plus I times 3 minus I. So that would be 3 times 3 minus I, and then I times 3 minus I. Right, so I'm just doing distributive property, which would give me 9 minus 3i plus 3i minus I squared. Since it's conjugates, we're not surprised that that cancels out. And this I squared becomes a -1. So I have 9 minus minus 1, which becomes 9 plus 1, which is 10. So my denominator becomes a 10. Now, if you want to do the box method, this is what that would look like. I would have 3 times 3, which is 9. 3 times I is 3i. Then right here, I would have -1i times 3, which is -3i. And then -I times I, which is -I squared. See how the middle terms will cancel out? And also, that would become a +1. Either way, I get 10. Now, on my numerator, I just distribute. And I do 2 times 3, which is 6. And 2 times I, which is -2i. However, in this case especially, I'm not finished because I can reduce my fraction. Okay, so we will try to reduce our fraction. Sometimes we won't be able to, but these are all divisible by 2. Okay, so to reduce our fraction, I think they're going to prefer for you to break it apart. So that's what I'm going to do. I'm going to do 6 over 10 minus 2i over 10. Okay, so all I'm doing is making sure this 10 goes to both pieces, right? It's kind of like a heart. And then I reduce. So 6 over 10 reduces to divide by 2, so 3 over 5. 2i over 10 reduces to I over 5. Okay, so this would actually be my final answer. Now, we're going to do some on your homework like that to practice a little bit more. All right, so let's look at some of your homework problems. So this is like example 15. I'm sorry, homework 15. And here's our answer, but I'm going to show you how we get to that. So, and remember, you'll have a similar question, just different numbers. So I'm going to multiply by the conjugate. And the conjugate of 6 minus 9i is just 6 plus 9i. So I multiply the top and bottom by 6 plus 9i. Now, on the denominator, I know that the middle terms are going to cancel out. So really, the shortcut is to just multiply the 6 times the 6. And the -9i times the +9i, which would give you -81i squared. And then, of course, that I squared becomes a positive, makes it become a positive because the I squared becomes a negative, and it's a double negative, right? And so that would be like the shortcut. But you can work it all out. The middle term should cancel out. So I'm going to add 36 plus 81, and that's going to give me that bottom number, which is 117. All right, so 117 on the bottom. And then on the top, I just distribute, and I get 3 times 6, which is 18. 3 times 9 is 27i. And if you look, you can see that that's not the right answer, right? So it's because we can simplify this. And if we can, we have to. So we're going to reduce this, and we're also going to break apart our fraction. And it kind of is like a heart. So I'm going to do 18 over 117. And I'm also going to write it as 27i over 117. And then I reduce those. So 18 is divisible by 9, and so is 117. So I'm going to divide the top and bottom by 9. So 18 divided by 9 is 2, and 117 divided by 9 is 13. Now, I don't expect you to know that off the top of your head. Feel free to use a calculator. If you type in 18 over 117 and your calculator should reduce it for you, you get 2 over 13. 27 and 117 are also both divisible by 9. So I end up with 3i over 13. So you can see that's how we get that answer. All right, let's try number 16. It's like your homework. So I have 5 plus I over 5 minus I. My conjugate of the denominator for 5 minus I, the conjugate would be 5 plus I. So I'm going to multiply the top and bottom by 5 plus I. And so on the denominator, really what's going to happen is it's going to be 5 times 5 and then I times I, because the middle terms will cancel out. So that becomes 25 minus 1, which becomes 26. So 26 is on the denominator. Now on the top, I'm going to multiply 5 plus I times 5 plus I, which I'll do over here. So it's going to take a little bit of work because it's a binomial and a binomial. So I'll do 5 times 5 plus I. So I'm doing distributive property, but I could also make a box. Plus I times all of that. And so that would be 5 times 5 is 25 plus 5i plus 5i plus I squared. When I add the two 5i's together, I get 10i. The I squared is going to become a negative 1. And so now I can combine the 25 minus 1, which is 24. So I have 10i plus 24. 10i plus 24. Once again, I can see that's not the right answer because I can reduce it. Once again, I'll break it apart. I'll make like a little heart and break it apart. So I'll have 10i over 26 plus 24 over 26, and I'll reduce these. So 10i over 26 would reduce to 5i over 13 plus 24 over 26, which would be 12 over 13. Now, if they require you to write it in standard form, then we want we want the real part to lead. So that's why I would probably rearrange this as 12 over 13 plus 5i over 13. Remember, they like you to write it in that a plus bi form where the the imaginary part is second. All right, let's try another one. Okay, this one's not as bad because we just have an I in the denominator that we want to get rid of. So if we just have an I and it's not a binomial, we can just multiply the top and bottom by I. And so on the bottom I would have I squared, and on the top I would distribute, and I would have 7i minus 4i squared. But I know that I squared, these I squareds will be replaced with a negative 1. And so I end up with 7i plus 4 over a negative 1. But we won't leave it like that, right? Because it's a negative. There's a negative 1 on our denominator. So what we can do is we can still separate it, I guess. That's what we'll do. We'll separate it like we've been doing. So we'll break apart the fraction, and then 7i over negative 1 is negative 7i. 4 over 1 is negative 4, and then to write it in the a plus bi form, we just need to rearrange it to negative 4 minus 7i. All right, we got a few more from your homework, and then we'll start talking about the quadratic formula. All right, so for this one, we have 6 plus 12i over 2i. And we want to get rid of that I. And one thing you could choose to do on this problem is they are all divisible by 2. So I could reduce by 2 before I even start. It's kind of your choice. Or you can just multiply the top and bottom by I right away. I can't help it. I see that they're all divisible by 2. So I'm going to rewrite this as 3 plus 6i over I. So all I did was divide all by 2. Couldn't help it. Okay, so now I have 3 plus 6i over I. I still have to get rid of the I in the denominator, though. So I'm going to multiply the top and bottom by I. And I times I is I squared. That was the whole point. So that will be a negative 1. And then up here, I'll have to distribute. So that'll be 3i plus 6i squared. So that becomes 3i. And then this I squared becomes a negative 1. So that's 3i minus 6 over negative 1. And then I apply the negative 1 to both pieces. So 3i over negative 1 minus 6 over negative 1 becomes negative 3i. And then a negative over a negative becomes a positive 6. I rearrange it to be 6 minus 3i. You can see that's the format they want you to write it in. All right, I think we have one more from your homework, and then we talk about the quadratic formula. So this is a pretty interesting problem, and there weren't really any examples that we had like this, so I wanted to make sure to do it together. So for this problem, I need to simplify each of these pieces. So I'm going to rewrite this as I square root of 5, and I'll rewrite this as I square root of 10. So all I'm doing is I'm taking the negative out by writing an I. Okay, then I'll multiply I times I, which is I squared. So outside times outside. And then 5 times 10, which is 50. Now, I know I squared becomes negative 1, and then I'm going to simplify 50. So when I simplify 50, I basically get 5 times 5 times 2, and I'm able to take out a 5. But there's already a negative 1, so this becomes negative 5 square root of 2, as you can see right here. All right, so we're now going to talk about the quadratic formula. We'll do a few examples of those, and then I think we have like one more that we do from your homework. All right, so we have many methods we can use to solve quadratic equations. We have solve by factoring, we have the square root method, we have completing the square, and now we have the quadratic formula. Quadratic formula is very useful in the sense that it allows us to solve every quadratic, whereas like factoring, we can only solve quadratics that are factorable. So if we have an equation ax squared plus bx plus c equals 0, then we can use the quadratic formula. That is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Notice that we get a, b, and c from the coefficients of our quadratic, and it always has to be set equal to 0. All right, so let's try some examples together. I'm going to rewrite the quadratic formula for you. All right, so for number 1, call this number 1. The first thing I want to do is identify a, b, and c. So a is equal to 1, b is equal to 3, and c is equal to negative 6. And so all I've done is I look at the coefficients, and in front of x squared is a 1, in front of x, or r, I'm sorry, I should say r, is a 3, and then the last part is a negative 6. Okay, so remember, that's how I get a, b, and c. I get it from my coefficients. And now what I'll do is I'm going to plug this into what I call the skeleton formula. So I'm going to have negative plus or minus the square root of something squared minus 4 times something all over 2a. So I call this the skeleton, and I'm just going to be plugging my values in. So for a, I'll plug in a 1, and a is 2 spots in the quadratic formula. So I'm going to plug in, and I'll do this in red. There will be a 1 here and a 1 here. All right, now for b is equal to 3, and b is in 2 places in my quadratic formula. So I'm going to plug in 3 in those 2 places in blue. So 3 will go here and here. And so all I'm doing is plugging it in. And then c is negative 6, and it only goes in the quadratic formula in 1 place. and that is right here. Now, what I'd like to tell all of my students to do is to just take a moment to figure out what the discriminant is. The discriminant is the b squared minus 4ac. It's this part of the formula because it's going to help us determine what kind of solution we're going to have. And what I've noticed is that if we have issues finding that number, everything falls apart. Okay, so off to the side, I want you to figure out what this number is. You can use a calculator if you would like. You can do it by hand. You could do both. But whether you use a calculator or you do it by hand, that's a very important number. So I'll show my work by hand, but I'm going to check it with my calculator. So this would become 9 and then minus negative 24, right? So 9 plus 24, which is 33. All right, so what does that mean? That means that this whole part inside the square root is actually going to get replaced with the 33. And this negative 3 I can just rewrite as negative 3. And then 2 times 1 is just 2. Now, the good news for us is I can't simplify this because 33 is just 11 times 3, and I can't reduce my numbers. But I want you to keep in mind that we can always break this apart, and sometimes we'll have to reduce our fraction. So I'm going to break this apart just like we did before. I'm going to put the negative 3 over 2. And then I would have plus or minus the square root of 33 over 2. And if I could reduce these numbers, and if there was a number on the outside and I could reduce it, I would. But I can't. It's just, there's nothing else I can do here. But I do want to point out that this is also 2 answers. So negative 3 over 2 plus the square root of 33 over 2 would be 1. Negative 3 over 2 minus the square root of 33 over 2 would be the second one. All right, so that's how we use the quadratic formula to solve a quadratic. Let's try another one. So for this next one, you can see that we don't have it set equal to 0. So we always want to set it equal to 0 first. So the negative 14 will have to be moved over. And when I move it over, I just change its sign and I set it equal to 0. All right, now I can start defining A, B, and C. So A will be 1, B will be negative 10, and C will be 14. And then what I'm going to do is, same idea, I'm going to do the skeleton of the quadratic formula. So that's negative B plus or minus the square root of something squared minus 4 times something something all over 2 times something. Okay, so this is what I call the skeleton. Now I'm going to plug my numbers in. So in my quadratic formula, so once again, looks like this. For A, I have A in 2 places, here and here. And then for B, B is in 2 places. And then for C, C is just in 1 spot, right? It's just going to go right there. There we go. Okay, once again, I would find this number first. This is a very important number that I want to make sure I get correct. So I would go off to the side, I would use a calculator, I would double check. I'm going to show what it would look like by hand, but please make sure to verify with your calculator because even I make mistakes sometimes. And just a heads up, if you're doing negative 10 squared into your calculator, make sure to wrap it in parentheses just as it's written right there. Okay, so I'm going to get 100 minus 56, which is 44. All right, so that 44 will be replacing this whole piece, okay? So plus or minus the square root of 44 all over 2 times 1. And then I'm going to clean this up right here. Do you see this double negative? See, this time B was negative, and in the formula, it's a negative B. It's the opposite of B, right? So the fact that it's a negative negative does make that a positive 10, all right? So that makes sense because B is negative, and in the formula, it's negative B, or opposite B. So B becomes positive, or I shouldn't say B becomes positive. This part right here becomes positive. Okay, now I have more work to do. Because it happens to be the square root of 44, I actually can simplify 44. It's 4 times 11. And so I can actually take out a 2, and I can replace the square root of 44 with its simplification. So we couldn't do that on the last problem because it was 33, I think. But on this one, we do have to simplify it if we can. So 2 squared 11 is the same thing as the square root of 44. So I did have to reduce that, or had to simplify it. Now I'm going to reduce, I'm going to break apart and reduce my fraction. This is a great example of when you can reduce it. Okay, so I'm going to make the little heart. The 10 is going to go over the 2, and the 2 squared of 11 is going to go over the 2 as well. Okay, so I break it apart. So 10 over 2 plus or minus 2 squared of 11 over 2. I can see that 10 over 2 reduces to 5. And when I simplify this piece, I'm not allowed to touch the 11. The square root of 11 is like its own personal thing. We already simplified it up here with the square root of 44. But I can reduce my numbers, the 2 and the 2. Okay, so that's going to reduce to 1. So I'm going to get plus or minus the square root of 11. So that is 2 answers. It's 5 plus the square root of 11, and it's 5 minus the square root of 11. Okay, let's keep going. So one of the benefits of being able to solve a quadratic equation is that we're able to get complex solutions. So we're going to do the quadratic formula again, and then we'll have just one more that we'll do that's like your homework. All right, so here's my quadratic formula. A is equal to 3, B is negative 2, and C is 5. All right, so I'm going to do the skeleton like we've been doing. Okay, I'm going to plug in A. I'm going to plug in B, which is negative 2. And I'm going to plug in C, which is 5. Right, so that's like my skeleton. I plug in the numbers. And then I like to find this number first. That's called the discriminant. It discriminates what kind of answer we're going to have. So I go off to the side. I just want to make sure I have this correct. So negative 2 squared minus 4 times 3 times 5. That would be 4 minus 60, which is negative 56, right? And let me verify that with my calculator. Okay, great. So negative 56 is going to replace all of this, right? So I'm going to have plus or minus the square root of negative 56. This double negative here, we're going to clean that up. Once again, in the formula it's negative b, but if b is negative, it makes sense that that part is going to become positive. So that does become a positive. 2 times 3 is 6. Okay, now we're ready to go. We have to take a look at our radical, and we have to simplify our radical. So I'm going to have to simplify the square root of negative 56. Now the first thing I notice is, oh no, there's a negative. That means I've got to take out the I. Then I'm going to go ahead and reduce 56. So that would be 8 times 7. Okay, and then I'm going to keep going. So I get, okay, yeah, 8 and 7, and then that would be 4 times 2 times 7, which would give me 2 times 2 times 2 times 7, right? Okay, so I can take out a 2. There's already I there, and then look what's left over. That's kind of cool. 2 times 7 is 14. Okay, so all that work just to simplify this piece. Okay, this piece and this piece are equivalent. So I'm going to write this as 2 plus or minus 2i. Let me make that look a little prettier. Square root of 14 over 6. Okay, now I'm almost done. I have to break apart the fraction. So I can write this as 2 over 6 plus or minus 2i over 2i squared of 14 over 6. And then I'm able to reduce my numbers. Let me highlight this for you. I'm going to reduce these numbers and these numbers. All right, so 2 over 6 becomes 1/3 plus or minus, and then 2 over 6 is also 1/3. But since it's going to be a 1/3, I'm going to have to write it like this, right? Because we don't necessarily, we know there's an invisible 1 right there, right? That green is really invisible. So that does reduce to 1/3, and of course this reduces to 1/3. So that would be your answer, which could also be broken apart as 1/3 plus I square root of 14 over 3, or 1/3 minus I squared of 14 over 3. Those are your two answers. Whew. All right, we got one more. This is like number 22 on your homework. It is a word problem. So we're going to do this one together, and hopefully it'll help you on your homework. All right, so this says the floor of a one-story building is 14 feet longer than it is wide. See the figure. The building has 1395 square feet of floor space. Write an equation for the area of the floor, and then find the length and width of the floor. Okay, so we need to think about the area first. So we know the area is length times width. So we have W times W plus 14 is equal to 1395. Okay, so area is length times width. We've got our length times our width. And so this would be, this part of my homework would be to just write that equation. Now the second part is to actually find the length and width. And so what I'm going to do is I'm going to have to work this out. And this does turn into a quadratic pretty quickly because I have to distribute. So I end up with W squared plus 14W equals 1395. And then since it's quadratic, I want to get everything on one side of the equal sign. So I'm going to subtract the 1395. Now, when you get to this point, you have choices. Actually, even at this point, you had a choice. You could complete the square if you want to. You can try to factor it, or you can do the quadratic formula. Okay, there's just too many options here, right? I think that if I try to factor this, well, 1395, let's see. If I know it ends in 5, so maybe I can do the obvious thing and just divide it by 5 and see what I get. Okay, 279, and that's not going to help me. You know what? I think I'm gonna erase this, and I'm actually going to complete the square for this problem. I think that would be kind of fun. Okay, so to complete the square, it's kind of already set up to complete the square, which is why I think we should try to do that. So what I'm going to do is I'm going to do plus blank here. So I'm going to set it up for success, plus blank here, and then right under here, I'll put a squared. So if you remember, what we're going to do is we divide the 14 by 2, and that number goes here, and then we square it, and that goes here, right? And what we do to one side, we have to do to the other. So I end up with 1395 plus 49, which is 1,444. All right, now I can get ready to solve. All right, so I'm going to take the square root of both sides. And when I take the square root of 1,144, I'm going to use a calculator for that, okay? So if you take the square root of that, you should get a perfect square. You should get 38, which is real nice. Okay, so I get plus or minus 38 is equal to W plus 7. All right, so then, and so this time, like, the radical went away. So when I solve this, when I subtract 7 from both sides, I'll be able to actually find the two numbers. Okay, so this is going to be basically negative 7 plus or minus 38. But that's really negative 7 plus 38 and negative 7 minus 38, right? And so what happens is when I do negative 7 plus 38, I get positive 31. When I do negative 7 minus 38, I get negative 45. Well, that answer is out because if you think about it, we cannot have a negative distance. So I have to just disregard that answer. I know it's kind of sad. So my solution is actually going to be 31, but 31 is just the width, okay? So the width is 31. And if you go back to the picture, we're referring to this part. So if this is 31 and it says that the width plus 14 is the length, then I can just plug 31 in there. So 31 plus 14 will give me the length, and that is 45. Okay, and the way that I would check this is I can do 31 times 45, and I should get 1395. All right, so that's how I'm going to check this. I'm going to do 31 times 45, and I get 1395. Great. Okay, so that is a crazy homework problem, but you can complete the square if you want to. It's kind of fun. Or you could do the quadratic formula as well, but the square root would go away and you'd have to reduce those numbers. All right, I hope this video helps, and I hope you have a great day. Bye.